Hey everyone, welcome back to mini lecture number 9 for Computer Science 252 at the University of Wisconsin, Eau Claire. In this mini lecture, we'll be talking about networking and protocols. Now, instead of reading some chapters or sections in the book, I wanted to give you something a little bit more engaging. So read one of either of these two pages. They're not too long, I promise. Well, the Catherine Games is a little bit longer, but it's more interesting, I think. So the first one is basically talking about two different internet protocols, which we'll lightly discuss in this presentation. And it talks about them in the context of gaming. Two different things that you could use for gaming, which one is better? And then the next one is talking about the different layers of networking and everything. We'll talk about that in a little bit too. But it basically gives a really good analogy. So I encourage you to read one of either of those. That's your homework for today. As for self-check questions, because this is kind of taking a different tack than anything we've done in our class so far, there's really no self-check questions. Do you know what the internet is? Okay, good. Let's move on. Network connections. The basic idea behind all networks is that you have a client and a server in some sense, and the client makes requests of the server and the server sends data. It's different for different kinds of networks, protocols, topologies, and everything, but this is the basic idea. And we're going to explore this in a little bit more detail on the next slide. Now, before we think about how a server and a client talk to each other exactly, it's helpful to think about the postal service analogy. Now, if you look at either of those two links on the bottom of the title slide, those will explain this in more detail. And it's really useful and worth it. But here's the basic idea. When you send a letter, you first type the letter, then you address it. But when you address it, there are certain rules you have to follow in terms of how the format of the address is done. Then when you put that into the mailbox, that's the end of your responsibility. You could put it in the mailbox, you could be a family member who puts it in the mailbox, but once it's addressed and ready to go out, it gets put in the mailbox and then it's out of your hands. Then that gets sent via trucks, planes, people just walking around maybe. You don't care how your letter is going to get to the final destination, you just care that it does. And so you trust that the Postal Service is going to take care of it, assuming that you've correctly addressed it. Now, hopefully, if everything goes well, it will get delivered into somebody else's mailbox. It'll be brought there by some letter carrier, the Post Service person. They will drop it off in your mailbox. Then from the mailbox, you can open it up. You see who it's from. Maybe you're like, this looks like spam. I'm just not going to open this envelope because it's another credit card offer. Or maybe you're like, hey, this is from my great aunt, whoever. This is really cool. I want to read it. And so then you open up and then you get the message. That's how it works with the Postal Service. Let's see how that works with computers. Now, suppose that you're trying to ask Google for a search term. So you're typing in, what is a blue gold on your on Google Chrome on your laptop, and you're trying to connect to Google, their webpage. So what happens is your application, Google Chrome, is in the application layer. Now, this model with these different layers was developed in the 1960s by the DoD, Department of Defense that is, as a way of kind of standardizing and understanding how the networks communicate to each other. What part of the computer is responsible for what part of the data and doing what things. So if you type in what is a blue gold to Google, that's all done in your browser in the application layer. That application will then try to create a socket and a connection to Google's servers. Now when it does this, it's going to do this via some internet protocol. So in the case of a browser, it'll use TCPIP, which is a certain protocol, which we'll talk about soon, but it's different than this model, which is just a simplified way of understanding it. So it'll use some protocol, some kind of transport mechanism, some library to make sure that that gets to its final destination. Now, really, the transport layer isn't so much actually doing the transport. What it's doing is it's doing the error checking. So did you type, it's going to take care of making the connection for your application, so your application doesn't have to worry about it. But it's not going to do all of the details by itself. It's going to call other layers. So it's going to make the connection. It's going to make sure that the application is asked for a valid URL, and it's going to make sure that it's going to package the data that your program sent the request for, and it's going to ship it off, and eventually it's going to unpackage that too. But for now, it's just shipping it out. It's like putting this addressing the envelope. The network layer then is basically when you put it in the mailbox. So it's basically the interface where the computer says, okay, how am I going to get this out there? It wants to send something to a specific computer at a specific network address. It doesn't care how it gets there, but it's going to package whatever the TCP protocol, in this case, sent, and it's going to make sure that it gets to that computer somehow. Now the data link layer is where your computer on its lowest level is saying, okay, I am maybe the modem, and I'm going to convert these software requests, with this, to send this thing to this destination. I'm going to actually send that to some other physical computer with a certain physical MAC address. So it knows how to talk to the wires and stuff in your computer that will eventually go out to your modem, to the router, to the outside world. That's kind of like the Postal Service, who are actually doing some of the transport. They're getting it and making sure it gets to where it needs to go. Then it goes to the media for data transfer. That would be like the truck drivers who drive, mail trucks, or the pilots who fly mail planes. They know that they actually, in this case, they might not know what they're driving, or what the cargo is in their truck, or whatever they're carrying. They just know that, well, I need to bring it from point A to point B. So the media from data transfer, like an Ethernet cable, a fiber optic cable, other wires, or wireless, they don't care what the ones and zeros are that they're sending. They just know that they got to transport it. So they do that, and then they bring it to the data link layer. And the data link layer says, okay, I've got this. Sure enough, this is for me. It's basically the Postal Service workers who are taking the mail and then putting it into a mailbox for a certain computer. The network layer is basically saying, okay, is this really for me? If so, how can I package it and understand it and bring it to the transport layer? The transport layer, again, is, in the case of TCPIP, it's going to take all that data and say, okay, well, what process requested this particular thing? Because there might have been a lot of requests to a Google server, right? What process requested this? What are they actually doing? Let's take these ones and zeros, convert them maybe to a string or something, and send that to the application layer. Actually, the interpretation is up to the application. So then the application will then say, okay, what are these ones and zeros? It's the actual process on the server, and it's going to basically take care of saying, what are these commands, what do they do, and then handling it appropriately. And then usually the web server would then initiate a communication to the laptop with a reply, and then this whole thing would go backwards in reverse. Those arrows would flip. So that's a long analogy, but that's what's going on. There are other things as well. There's an OSI standard. You can see more about that, but again, this is just the TCP/IP model. We talk about like a web stack or a full stack developer. A full stack developer is someone who's going to be working at all levels of a web server, anything from working on Ethernet stuff all the way up to developing web applications, or maybe working on some of the stuff in between. But that's basically the different protocols, the different mediums that each of these different layers they use. So here's a server, here's a client. What do each of them do? The server establishes communication endpoints. So it's saying, here I am, I can do things. And that's what it does, its first job. Second thing is, once it says I'm here, I'm doing things, it waits for the connection from the client because it wants to provide the service. The client then will initiate communication with a server, so it will request that service. The server will send and receive data after accepting that connection with the client. It will send, receive data. Client will send and receive data. It could go the other way as well. And the server can communicate with many clients. The client, okay, so your laptop is probably communicating with many servers right now. Maybe a time server, maybe an internet server. Right now, probably a YouTube server, right? Because you're watching this on YouTube. So you can communicate with many different servers, but each process is only going to be talking to usually one server at a time. Now, there's fancier things too, but for a given operation, each client will talk to one server. A server, on the other hand, can talk to many clients, providing the same service to many of them at the same time. So in order to do all this communication, the servers and the clients all need a language to communicate, because ultimately it's all ones and zeros. And how do I know what your ones and zeros mean if you're trying to give me a message? Are you, it'd be like writing in a different language. How do I know what is acceptable? What's the standard here? The standard that we use is called a protocol. So there's lots of different internet protocols. But in short, a protocol is an agreement about the packets exchanged by the communicating programs and what they mean. Now it's not just about the packets, we haven't even talked about what a packet is, it's about what the ones and zeros mean. And each of those different layers that we talked about on the previous slide has a different protocol for how to transport information from one computer to another computer. An Ethernet cable has its own protocol. When I send ones and zeros on an Ethernet cable, what do those ones and zeros mean? Do they even make sense? Well, there's rules about that. You can't just send any ones and zeros. And so on. The transport layer, the network layer, the application layer, they all have rules about how to handle things. Ultimately, each of these protocols tells how the packets or bundles of ones and zeros are structured. They say things like where the destination information is located in the packet. How big is the packet? Is it a tiny little packet with just a little bit of information, or is it a big gigantic one if you're downloading a file? How is the information to be interpreted? That's another one. All protocols are designed to fulfill a specific task. So because of that, or because there's a lot of different kinds of tasks, there are also a lot of different kinds of protocols. One of them is HTTP. So it's the protocol that governs how hypertext objects, or HTTP documents, are transferred between a web server and a web browser. TCPIP is actually a family of suites. There's the parent protocol, which is IP, Internet Protocol, and that's basically, it does a number of things, but it basically sets the rules for how you address another computer. So IPv4, Internet Protocol version 4, it describes this a web address or an IP address. These are the 4 dotted IP addresses that you're probably familiar with. Now, because we're quickly running out of IP addresses for all of the world's devices and smart devices and whatnot, we've invented IP version 6 to replace it. And this, instead of having 4 bytes of values that we express using that dot notation, instead it's 128 bits, and so 32 bits to 128 bits. There's 8 sets of 4 hex digits separated by colons. So that's the new IP address there, the long one. And because there's so much more information there, now we can have almost as many as 1 times 10 to the 38th power. So 100 trillion different IP addresses could be covered by IPv6. So what about the 2 child protocols? They're both based on the Internet Protocol, IP protocol. We'll talk and compare those two because they're pretty often used in software development. So we'll address those in a separate slide in just a sec. Another protocol that's pretty common is FTP, File Transfer Protocol. So if you want to transfer files from your computer to another computer or vice versa, you can do that using FTP. And there's a lot of other protocols as well. Let's look a little more at IP addresses. If you're using Linux, you can get some information this way. If you're on Mac, this command right here will give your IP address. Windows, this will give you a bunch of information, including your IP address. Now, there's a difference between all of these, which may give you your private or public IP addresses, which you might have a different IP address on your private home LAN or wireless network, but that might be different than the IP address you have visible from the world. And your router will take care of a lot of that translation for you. Now, if you want to see what your IP address is relative to the world, you can use like a third-party source. So this gives your public IP address. Of course, you need the curl command to do this, but you're basically saying to the server, the ipinfo.io server, what is my IP address? And the IP server will look at your packets and say, this is from this address, and then it'll echo it back to you. So that's a nice little command. You could even create a script, a bash script, to do this. It's a one-liner. So we talked about the FTP, File Transfer Protocol. Here's some sample commands that your client might send to the server. And it will send it as just ASCII text. It can send user name, it can send the password. The server can say, give a status code 331, username okay, but you need to enter a password now. If you want to list all the files in a current directory using FTP, you can do that. You can ask to get a file, you can ask to put a file on the server, and the server can tell you, that's working, that's not working, and so on. So that's kind of how these communications might be for this one particular protocol. I mentioned TCPIP and UDP before and said we would discuss them. Here we go. TCPIP gives a reliable connection with a couple caveats. But basically what it does is it guarantees delivery of the data. So if packets are lost, it's going to make sure it resends them. And it's also going to do route finding and tracing. So as long as there's some kind of network connection between you and your destination computer, that computer could be, in the bottom of the ocean, it could be up in space, but as long as there's a connection of TCP/IP capable network devices connecting them, it will find a way to get there. UDP is not quite as reliable. It's going to send out packets or called datagrams, and it hopes it gets there, but it's not guaranteed. Usually, above 99% of packets will get to its destination, assuming that the path was possible. So very few packets are actually lost. TCP/IP is going to do extensive error checking. Okay, was there a packet that got lost? Well, let's resend it. Was there a packet that looks corrupt? Well, let's resend it. So it does a lot of error checking that way too. UDP is only going to do simple error checking. In TCP/IP, packets will arrive in order. So if you send out a packet, like via Google Chrome, your browser, that uses TCP/IP. So if you send out a request to Google for a web page, that request with all of its information is going to arrive at Google's web servers in order. So the application isn't going to have to make sure that they're all in order. TCP/IP is going to take care of that for you. So it's what we call a stream-based protocol. First in, first out. UDP, on the other hand, is going to send packets, and they're going to arrive whenever they arrive. So some packets might take this route, some packets might take a slower route, some packets might find an even faster route, and so they're going to arrive when they arrive. And it's up to your application to determine, do I really need these to be in the right order or not? Maybe you do, maybe you don't. Now you may be thinking, oh, why should I ever be using UDP instead of TCP/IP? Well, TCP/IP is much slower than UDP. TCP/IP, because it does all of this reliability, error checking, and sequencing, it's a lot slower. Sometimes it's like, hey, there's a couple packets that got lost. I have to, request those packets to get sent again. And when it does that, it has to wait for it. Also, TCP/IP, the header bytes are a lot bigger. There's a lot more information in the overhead. That helps with the error checking and so on. UDP is, on the other hand, much faster, and it's very lightweight. So there's only 8 bytes in the header as opposed to 20 to 80 bytes. TCP/IP does not support broadcasting, and I'll talk about that in a sec. TCP/IP doesn't support broadcasting. It's very much connection-based. So when you establish a TCP/IP connection, it's one computer connecting to another computer. There's always a pair of computers that are talking. And so that's well and good, but you can't broadcast your information to a bunch of different computers. And UDP, on the other hand, you can. So UDP acts a little bit more like a TV broadcast antenna or a radio broadcast antenna. So it will say, here's my information, and anyone who's listening can pick it up. So there's not really a concept of a connection. There's not really, you could say like, well, the TV is connected to the broadcasting antenna. Yeah, but it's not really as strong of a connection as like, a phone talking to another phone. So because of this, TCP/IP is used for things where sequence and error checking matter. So if you're making a web browser request, that matters. If you're trying to get a file, it certainly matters that you get the file pieces in the right order and that you don't have any errors. Same thing for SSH and email. You don't want those things to be out of order and you don't want them to be corrupt. UDP, on the other hand, when those things don't matter, you can get more performance out of them. So it's great for voice over IP, streaming audio and video, because if if one of those packets is missed, maybe there's a tiny little blip, but it's fine. You've moved on past that. It's also important for all kinds of time-critical applications where time and reliability matter. And so aircraft controllers, you might be like, well, why am I going to be controlling aircraft with an unreliable connection? Well, it's not so much that it's unreliable, it's just a different kind of reliability. It's more time reliable, whereas TCP/IP, if a packet gets lost, it has to resend it. And if that packet gets lost, it has to resend it. And so again, TCP/IP, you can have really, really long delivery times. Let's compare these briefly in the context of gaming. Now, I don't know if you will quite be able to see what this GIF animation is doing, but basically back in the day when I first started playing StarCraft 1 in high school, around like 2001 to 2005-ish, there was a whole lot of really pro gamers who would be playing StarCraft, and they would be clicking many, many times to give like a simple command. So if they were telling somebody to go somewhere, they would give that command 5 or 6 times. Now, StarCraft, I know, talks about actions per minute and being able to do a lot of things. This is a different thing than that. They were giving the same command many times as opposed to giving many commands per second. Why were they doing that? Well, it was because StarCraft was using a UDP connection. If you use a TCP connection for gaming, then if you lose a packet, you have to wait for it to be resent, which means you have to connect to the client and say, could you please resend that? And then the client has to say, oh, yes, I can resend that. And then you have to keep going. But what if the request to resend it gets lost? What if the resent packet gets lost? You have to wait again. And so it has a really, really long ping. So most games don't really use TCP/IP for most of the data that they transmit. Instead, they use UDP because it has much faster performance. So it'll send the data quickly. It'll send lots of little bits of data. And so for any kind of fast-paced real-time games like StarCraft or Rocket League is my favorite example, they will give you lots of little pieces of information that eventually will give you the full picture, but you might miss little tiny bits of it here or there, so things might have a little bit more jitter or something. So going back to the StarCraft example, people would be sending like 5 or 6 commands for a single action, not because they were trying to get the most commands per second, but because if one of those commands got dropped, they would still give the same command, and the server would eventually say, oh, you're moving this guy here and not to the other place. So it was a way of sending commands reliably. Now just to review, what are the layers of communication in the TCP/IP model? Why is a protocol necessary for internet communication? What is a protocol? Why is it important? TCP and UDP, what are some of the similarities? What are some of the differences? And what would you use for email, a first-person shooter, a call on Discord, or a program to remotely install software for a distant computer? All of these questions have answers at the very last slide, but I encourage you to pause here and think through them and write your answers down. As for a practice problem, there's none today. All of this stuff is way too complicated. We'll do a little bit of networking in a lab on Wednesday, but for now, don't worry about it. And here are the answers for the review questions. Now, I'm also going to give you a little bit of a teaser on the very last slide for what we're going to do next. What will we do next time? We'll answer these questions. How can we build a simple TCP server and client? And we'll be doing a little bit of this on Wednesday for our lab. What tasks must the server and client each perform? To what degree does the order of the bytes or the order of the tasks matter? And what system calls are involved? So that's it. Thank you for your time, and I hope that this has been helpful to you and useful, and I will see you next time. Goodbye.